Hi class. After some technical difficulties, we're back, and I believe we left off in the last video at number 3 on solving homogeneous systems. So we have dy is 2, 1, negative 1, 2 applied to y. And just as before, what we're going to do is to solve the eigenvalue eigenvector problem for the matrix, and then use this information to tell us what the solution for this system should be. So we start with a minus lambda I, and set the determinant of this equal to 0. So I'll put the 0 over here so it doesn't get mixed in. And we can see that we have this nice form, 2 minus lambda squared plus 1 equals 0. It's already a completed square. So to solve this, what we get is 2 minus lambda equals plus or minus, if I move the 1 over, I get negative 1. The square root of negative 1 is I. So rearranging this tells me that lambda is 2 plus or minus I. Now, in this case, we have complex roots, and we do something a little special with complex roots. We need to find the eigenvector corresponding to just one of them, and then use symmetry and Euler's formula to figure out the rest of it. So, to find the eigenvector, just use the one that's plus. If I plug this in, I get negative I, 1, negative 1, negative I. And if I call the vector components v1 and v2 as usual, then I get the two equations, negative I v1 plus v2 equals 0, and negative v1 minus I v2 equals 0. And at first, it may not be clear that these are actually the same relationship, but if we solve both of them for v2, we see that we'll get the relationship v2 is I v1. So to see that here, let's see, we should have v2 is, if I move this over, I get v1, and then divided by negative I. To clear the I out of the denominator here, I just multiply by I. So I'll get negative I over I squared times v1. But I squared is negative 1, which cancels the negative in the top. So in fact, I really do get the same relationship here. So that means what I'm going to call v plus is, well, the first component is v1, the second component is I v1. So we just get v1 times the vector 1i, setting v1 equal to 1. You don't have to, you can set it equal to 2 or whatever, but we're just going to set it equal to 1. We get 1i. Now, the remainder of the problem involves Euler's formula, and what we're going to do is we're going to take e to the lambda t, which in this case is e to the 2 plus I t, and apply it to our vector v plus. So I'll put a v plus over here, and over here we're going to get 1i. And for this part, I need to use Euler's formula. I'll have e to the 2t times cosine t plus I sine t applied to the vector 1i. And now all I need to do is to distribute this part into my vector, the Euler's formula part into the vector, and split real and imaginary parts up. So what I'm going to get is e to the 2t times the vector cosine t plus I sine t, And if I multiply through by I, I'm going to get I cosine t plus I cosine t. And I times I is -1, so negative sine t. Now splitting the real and imaginary parts up, I get e to the 2t times cosine t negative sine t plus I e to the 2t sine t cosine t. Okay, and this auxiliary calculation gives us our two solutions. This is one of them, and this part, the imaginary part without the I, is another real solution. So what we get, ultimately, is that y of t is c1 e to the 2t times the vector cosine t negative sine t plus c2 e to the 2t times sine t cosine t. So not too bad. We just have to do a few auxiliary calculations to get our solution. And here, ultimately, is our solution. Okay, let's do one more of these examples. This one happens to be number 4. We have dy is the matrix 2, 0, 0, 2 applied to y. And here we're going to see actually something really special happens. If we still start with the eigenvalue eigenvector problem, a minus lambda I, in this case, is just 2 minus lambda 0, 0, 2 minus lambda. So setting the determinant of this matrix equal to 0, I get that 2 minus lambda quantity squared equals 0, so that lambda equals 2. That is to say, we have a repeated eigenvalue of 2. There's nothing terribly special about that. We've seen this before. However, when we plug this back in, so if we try to find the eigenvector v sub 2, plugging in 2 gives us the 0 matrix. What this tells us, our equations are just 0 equals 0 and 0 equals 0. So we get no restrictions on v1 and v2. So v1 and v2 can be whatever they want. Well, I'd like to get non-zero vectors out of this, so I'm going to try to write it as much like what we were doing before. So first, I'm going to write this as v1, 0, plus 0, v2, to show that v1 and v2 don't interact. Next, what I can do is factor out v1 from the first one. And similarly, I can factor out the parameter v2 from the second one. This gives me two distinct eigenvectors for the eigenvalue 2. In this situation, all we have to do is just use these two eigenvectors in the typical formula. So we'll have c1 e to the 2t times the first eigenvector plus c2 e to the 2t times the second one. It's not the second eigenvector. And that's it. So that doesn't seem too bad. But let's take a step back and realize that we didn't actually need any of this matrix arithmetic to make this work. So recall that what this stands for, what this system stands for, is y1 prime, y2 prime equals, well, let's see, y is y1, y2. I'll multiply it out to show you. we have y1 prime equals 2y1 and y2 prime equals 2y2. I don't need anything fancy to solve this equation. So I'm going to put a little bar here and then do the y2's over here. They'll actually be exactly the same other than the subscripts. Here, this is a first order constant coefficient homogeneous linear differential equation by just writing it this way. The auxiliary equation is going to be m minus 2 equals 0, which tells us that m equals 2. So that y1 should be c, and we'll subscript it with a 1, e to the 2 x, or t, or whatever variable you want to use. And y2 here, it's exactly the same. And if you compare this to what we had as our solution, and maybe I'll use x's to show you that they're all the same, we had c1 e to the 2x times 1, 0, plus c2 e to the 2x times 0, 1. And if I just expand these out, that's c1 e to the 2x, and that's c2 e to the 2x. But y is the vector y1 and y2. So this tells us that y1 is c1 e to the 2x, which is exactly what we found there, and y2 is c2 e to the 2x, which is exactly what we find here. So while it may seem mysterious, this is actually a way easier case.